Now that we've examined aldol condensation reactions, we're going to look at some modifications of these reactions. And the first one that we're going to take a look at is what we call an intramolecular aldol condensation. And so we can get intramolecular aldol condensations if a molecule has two things. One, an enolizable hydrogen, obviously, and then in a different location on the molecule, a carbonyl group. And so when these two things happen, you can get intramolecular addition. Now, these are typically favored when you can form 5 or 6 membered rings, right? So when you're looking at in this case where we'd be talking about diketones or dialdehydes or an oxoaldehyde, where you can form an enolate uh, and and once that enolate forms, it can attack a carbonyl and form a 5 or 6 membered ring. Then that's what we say is a favorable product formation. So let's take a look at an example here where we have 2,6 octane dione. And if you notice in this particular structure, there are two enolizable hydrogens. And so there's two possibilities to form an enolate. Um, and uh, if we look at the structure, we see that the carbon on the end here at that methyl group certainly is an alpha carbon, and so it can form an enolate. Likewise, the carbon on the other side of the carbonyl can form an enolate as well. And if we number the carbons, starting with the carbonyl that's going to be attacked, and labeling it 1, we have 1, 2, 3, 4, 5, 6, 7. So we can form an enolate on the 7 carbon or on the 5 carbon. So let's take a look at what happens as a result of those enolate formations. So we react the diketone with sodium hydroxide, and enolate forms. Let's say that enolate forms on the 7 carbon. So now we get nucleophilic addition to the carbonyl, and we're going to form our 7-membered ring, right? Because there's 7 carbons now in that ring. And if we number that 7 carbon ring, 1, 2, 3, 4, 5, 6, 7, on carbon number 1 we have a methyl group and we have an OH group. And then on carbon number 6 we have a carbonyl. And that's an easy way of keeping track of where all of the substituents are located. And of course, if we heat this up, we can get dehydration, so elimination, to produce the alpha beta unsaturated ketone, the enone. And so notice in this particular example, if the enolate forms on carbon number 7, then we form a 7-membered ring. Now, if we take that same structure and treat it with sodium hydroxide and assume that the enolate forms are on carbon number 5 and we get nucleophilic addition to occur, now we're going to form a 5-membered ring. And so we can draw a 5-membered ring, and of course keeping track of all of the carbons, we start numbering 1, 2, 3, 4, 5, and on carbon number 1 we have again a methyl group, and we would have an OH group. And then on carbon number 5 we have carbon 6 and 7, which is a carbonyl with a methyl group coming off of it. And so this structure looks like this. And of course this also, carbon number 5 has is an alpha carbon, and so you can remove a proton from it and undergo elimination. And if we look at the two structures, we have a possible 7-membered ring, a possible 5-membered ring. That 5-membered ring is going to be the favored product. And so we may get some of that 7-membered ring forming, but the major product is going to be the formation of that 5-membered ring. All right, let's take a look at another example. Here's an interesting example where we have a diketone treated with sulfuric acid and water, and it can undergo an intramolecular aldol condensation reaction. And notice if we examine this particular structure, there are four alpha carbons. And of course there's symmetry in this, and so interestingly enough, with this particular example, all give the same product. Now, that doesn't happen all the time just for this particular example, so we have to be careful about whether or not we can get a mixture of products or not. And so if I assume this particular carbon attacks the forms an enolate, well, it would form an enol in this case because it's under acidic conditions, and attack the protonated carbonyl, then I can close the ring. Notice I get a 7-membered ring on the left and I form a 5-membered ring on the right. My beta hydroxyketone in this case, and of course I can get elimination to occur to form my alpha beta unsaturated ketone like so. And so this is a way to form enones that are cyclic. A very interesting little thing to think about. So when we have cyclic enones, you should be thinking intramolecular aldol condensation reactions. Now, another twist on aldol condensations is doing what we call crossed aldol condensations. And in general, crossed aldol condensations, or sometimes we call them mixed aldol condensation reactions, yield multiple products. And this is kind of the downside to crossed aldol condensations, is the idea if we simply took two aldehydes, added sodium hydroxide to them to get them to condense, you get multiple products. So, for example, if I took butanal and propanal, mixed them in an ethanol solution, and added sodium hydroxide, what would I get? Would I get the enolate of propanal reacting with butanal, or vice versa? Well, the answer is that I get a mixture of products, and the reason for that should be apparent to you. The big reason is that two enolates can form, right? I can form the enolate of butanal, or I could form the enolate of propanal. And if we think about the products, just kind of for practice, thinking about all of the possible products that can result from this mixture of only two aldehydes, if I take a look at the enolate of butanal and I react it with butanal, because remember, only a small portion of the enolates form of both butanal and propanal. The majority of reactant I have is butanal still in its native form, so to speak, and propanal. So the enolate of butanal can react with butanal itself to form the typical aldol condensation reaction of butanal, but it can also react with propanal as well. And so so we can form the aldol addition product of that reaction as well. Likewise, I can form the enolate of propanal as well. And of course, it can react with butanal to give a mixed aldol addition product. And of course, it can also react with propanal itself to give the typical aldol addition product of propanal. And so you see that there are 4 possible products that result in mixing two aldehydes together and simply adding sodium hydroxide. And this is not a feasible way of synthesizing any one of these, because in essence you get about a 25% mixture of each one of them, and so that's not a very good yield. Now, there are ways to successfully cross two carbonyl compounds, and one of the easiest ways is if one of the carbonyl compounds has no enolizable hydrogens. And so here's an example where I'm taking a ketone and reacting it with benzaldehyde. Now notice this particular ketone has an enolizable hydrogen, on the right-hand side of the carbonyl. On the left-hand side, there are no hydrogens, so I can't form an enol or an enolate on that side. But benzaldehyde has no alpha hydrogens. Remember, the hydrogen coming off of the carbonyl is not an alpha hydrogen, and therefore an enolate cannot be formed with benzaldehyde. So if I react this with sodium hydroxide, the enolate of my ketone is going to form, and it's going to undergo an addition reaction with the carbonyl of benzaldehyde. And upon condensation or dehydration, I'm going to get my enone, my alpha beta unsaturated ketone in this particular case. And the yields are actually very high typically for these types of reactions. In this instance, the yield is a 90% yield. Let's take a look at the mechanism of that reaction and see what's going on. And you should be able to kind of follow by now what's happening in this reaction. Obviously, the ketone has an enolizable hydrogen, like we said, and so we can remove that hydrogen, deprotonate it, forming our enolate. Right? So there is our enolate with the negative charge, and of course it's resonance stabilized, but I'm not going to show that. So you have the carb anion and the oxo anion as resonance structures. And in solution now, we have to be careful because there still are two carbonyls that can react. There's the ketone that's available because remember, the enolate is only in small concentrations. So there's the ketone and there's the aldehyde. Now, if we get a reaction of the ketone with the enolate, we form, so we undergo addition, and then upon dehydration, we get the enone that forms with the ketone. So this is only if we had ketone present. Of course, we don't just have ketone present, we have the aldehyde present as well. So that aldehyde could also undergo attack by the enolate, and we get this enone. Now, if we compare the two enones, the one at the bottom with the phenyl group is actually the favored product. And if we think about why this is the case, it becomes fairly apparent. So the first thing that we have to realize is that aldehydes, going back to reactivity of aldehydes and ketones, we already know that aldehydes are more reactive in nucleophilic addition reactions than ketones are, right? The ketone has the two alkyl groups that stabilize that carbonyl and decrease the electrophilicity. The second reason which is kind of related, is that the equilibrium of the addition to aldehydes is actually favored toward the product over that of ketones. And then the third reason is that the resulting phenyl substituted enone with the benzaldehyde is actually more thermodynamically stable than the product with just an alkyl group, right? So phenyl groups stabilize alkenes more than alkyl groups do, and therefore it leads to a more stable thermodynamic product. And these types of reactions where you're taking the enolate of a ketone and you're reacting it with benzaldehyde or benzaldehyde derivatives are a class of reactions called Claisen-Schmidt reactions. Claisen-Schmidt reactions. Now, there is also another way that you can effectively perform cross-Aldol reactions, and that is by simply creating the enolate of one of the carbonyl compounds completely, and we typically do this with LDA. So you take you take one ketone or aldehyde, treat it with LDA to form the enolate, and quantitatively, and then you can take that enolate and react it with another aldehyde or ketone and get aldol addition reactions or condensation reactions. So here's an example where I have 2-pentanone. I react it with LDA. Of course, my enolate quantitatively forms at the methyl carbon, simply, of course, due to steric effects. So now I have my enolate forming, and I can react that with an aldehyde, or I can react it with another ketone, and I can get addition and my product, right? So remember how to draw the product. So I draw the backbone of the aldehyde, because that's the one that's undergoing attack. The carbonyl gets converted to an OH group. I then add the alpha carbon of the ketone, and then add what's attached to it. And so I get my beta hydroxy ketones. And these are also in very good yields. I can get, between 60 to 90% yields of these types of reactions. Here's another example. Again, I'm taking a ketone, reacting it with LDA, followed by a reaction of an aldehyde. In this case, remember, again, steric effects are going to dictate where the enolate forms. I could form two potential enolates, but I'm going to form the enolate on the right-hand side of that carbonyl, again, due to steric effects. And the product looks like this. So you can see we can form some very creative beta hydroxy ketones or beta hydroxy aldehydes, and or alpha beta unsaturated ketones and aldehydes in a variety of ways using crossed aldol condensation or crossed aldol addition reactions.